This is review video 32, energy and reactions. So first of all, let's define energy really quickly. Energy is defined as the ability to do work. Now, it is described by an equation. You see that equation right here. We see that delta E, or the change in energy in any particular system, is defined as the amount of work that that system does plus the amount of heat that is transferred between that system and its surroundings. Work is just simply energy transfer when a force acts on an object, so that could be literally anything. We could be talking about force applied between molecules, we could be talking about a mechanical system where force from one part is applied to another part, or really anything. But in this class, we're going to focus obviously on chemical reactions, so we're going to think of work as the force between molecules. And then you're already a little bit familiar with heat as a concept because we know that energy or heat can come into a reaction or out of it depending on what's going on. Next, I want to talk about the first law of thermodynamics, which is also known as the law of conservation of energy. That has two main points to it. The first point says that the energy of the universe overall is a constant. But within that, energy can neither be created nor destroyed, it can only change form. So that should sound familiar to you because this piece of the law of conservation of energy is very similar to the law of conservation of mass, that matter can neither be created nor destroyed, only rearranged. But in this case, obviously, we're talking about energy, and we know that energy can change form because you would have heard this in middle school science before, that there are different types of energy. There's mechanical energy, chemical energy, which is what is contained within bonds, which is a form of potential energy. There's kinetic energy, which is the energy of movement, so on and so forth. So energy can change forms between all of those and more. There is also an equation that describes that law of thermodynamics, and it states that the energy of the universe is equal to the energy of any reaction system plus the energy of the surroundings of that system, which sounds a little bit ridiculous because there's a ton of reactions going on literally all the time. How can that be? Well, a reaction system is specifically the chemicals that are participating in that reaction, which is logical, that's easy. But a reaction's surroundings is literally everything else in the universe. That said, when we're looking at the energy transfer between a system and its surroundings, we only care mostly about the immediate surroundings of that particular system. We don't care about what's going on Jupiter, because though technically, yes, matter could theoretically move from Earth to Jupiter over the course of many, many thousands and millions of years, we don't really care about that when we're studying reactions. So again, a reaction's surroundings, while technically everything in the universe, we only care about what's right next to it. Okay? So a reaction system can be defined as open, closed, or isolated. An open system is like 99.9% of all reactions, right? Think of any reaction you've done in my classroom. You've poured chemicals together in beakers, you've heated things, you've cooled them off, you've done all manner of things. But basically what an open system reaction is a reaction system that exchanges both heat and matter with its surroundings. So if you're trying to cook something on the stove or boil water or whatever it is that you're doing, you're going to exchange heat in whatever reaction you're doing, and maybe some things splatter out of the pan, or something in the air kind of goes down into the pan and enters into the reaction, or whatever happens, because heat and matter can always be exchanged in an open system. A closed reaction system cannot exchange matter with the surroundings, but it can exchange heat. So an example of that would be anything that is done in a calorimeter. So if you contain the system, if you essentially put a reaction in a sealed box and it can't interact with its surroundings at all other than to transfer heat between it, that would be a closed system. And then finally, an isolated system can exchange neither heat nor matter with its surroundings. But the issue with this is it's really hard to have a true isolated system. That's more of a theoretical concept than it is an actual thing that we can do. There are ways to get close to a true isolated system in a lab setting, but definitely not in a high school lab. And again, it's very, very difficult because you have to isolate that reaction so hard from its environment that it can't even exchange heat with its environment, which again is near impossible. So an example of an isolated system would be literally our entire universe would be one isolated system that's incapable of interacting with anything outside of that universe. But otherwise, again, it's more of a theory than anything else. So open systems, again, that's going to be, both heat and matter exchanged with the surroundings. So if you were boiling water with no lid, you could exchange heat. You could feel the heat coming off of that boiling water and steam comes out of it. A closed system is not going to exchange matter, but it will exchange heat. So a pressure cooker, if you have like an instant pot, that would be an example of a closed system. If you touch the outside of a pressure cooker, it does feel warm, so you can feel that heat is coming out of that pressure cooker, but no food or other particulates are coming out of it until you open up that system yourself. Last but not least, I want to just reiterate endothermic versus exothermic. If you have an exothermic reaction, that means that heat or Q is coming out of that system and going to the environment. Your delta H value for that is going to be negative, and your potential energy graph is going to look like this, with our energy of our products being lower than our energy of our reactants. If you were to hold an exothermic reaction in your hand, it's going to feel hot or warm to you. On the other hand, if you have an endothermic reaction, that means that heat is going into that reaction system. So you have a positive delta H value, and our graph looks like this, with our energy of products being higher up than our energy of reactants. And if you hold an endothermic reaction in your hands, it will feel cold. The reason that happens is because since this reaction system is taking in heat, it's taking it from you if you're holding it. And so that's why it would feel cold to you, even though the reaction system itself would be getting warmer theoretically. If you have any issues understanding any of this, please ask me in class.